I'm delighted to be joined by Andrew Engel, who is a presenter. Andrew Engel is the Chief Data Scientist at Rasgo. He has been working as a data scientist and leading teams of data scientists for over a decade in a wide variety of domains, from fraud prediction to marketing analytics. Andrew received his PhD in Systems and Industrial Engineering with a focus on optimization and stochastic modeling. He has worked for Townsend University, the SAS Institute, the US Navy, WebSense, which is now ForcePoint, Styx, HP, and led data robots efforts in entertainment, sports, and gaming before joining Rasgo in 2020. Hi, Andrew.
Hello, thank you for having me. Thank you all for attending. So I know there's been a couple of questions. I'm happy to share the slides at the end of this, so we'll make those available to you. And there's been some questions about hands-on learning, and I do intend to do some hands-on learning, but we're going to split that over the course of 2 sessions. So today, we're going to talk about feature engineering and best practices and give you a sense of the techniques and the way I think about feature engineering. And at the same time, next week, we'll share some Python code and we'll actually walk through some feature engineering for a customer churn use case, so you can see how I would go about applying these best practices. So in the next roughly hour, what I'd like to quickly cover is why feature engineering. Why is it important? Why do we care? Why is this my favorite part of the data science life cycle? And then as a related note, what do I really mean as feature engineering? What is it? How do I think maybe the community is having some issues? Before switching into the best practices, what do I think about when I'm doing feature engineering? What should we worry about? And then finally, finish up with a lot of examples, ideas, ways you can think about doing feature engineering that summarizes all of what we've covered. So why feature engineering? When you go out and you talk to data scientists and you ask them, what do you do? The stereotypical response is, I spend 80% of my time on data prep and feature engineering. I find it a little funny that data scientists say that, and then they almost sound sad that they spend so much time there. So why is it so important? Well, I'm not just the only one who thinks it's important. Some very, very impressive gentlemen agree with me. Andrew Ng has recently stated applied machine learning is basically feature engineering. And in fact, if you've been listening to him or watching what he's saying over the last year, you've seen he's become very insistent on that data-centric view of machine learning and data science. It's about the data. Pedro Domingos, a professor from the University of Washington, at the end of the day, some machine learning projects succeed and some fail. What makes the difference? Easily the most important factor is the features used. Okay, so multiple people within the community are clearly saying feature engineering, what we're doing with our features is the most important thing. So why is this so important? In machine learning, you're building pattern matching tools. They're looking for signal in a very noisy data set. Anything we can do as data scientists to help those machine learning algorithms identify those signals and get a better model is useful. This can be things that are just mathematical in nature or signal processing in nature. This also can be taking the business knowledge of the stakeholders you're working with and turning it into something that the machine learning algorithm can actually use. Remember, the goal in all of this is to build better models, more accurate models, more predictive models. And the thing that I see a lot of data science teams struggle with is that the real goal is to drive business value. If I'm building models for a business, at the end of the day, What I need to do is drive that business value, provide value to my business, allow the business to make additional money or save money. And everything I do in that modeling process should be driven towards that goal. Feature engineering is one of the most important ways you can do this. And it's also one of the ways that you can mess up and cause your models not to work into production. So we'll come back to that as we discuss best practices. So what do I mean by feature engineering? I find it somewhat amusing, again, that when I talk to data scientists, they talk about, well, what I really want to do is model building. I want to train my models. I want to do my hyperparameters tuning, but I spend 80% of my time again in that data prep phase. And then when you do a Google search for feature engineering, what do you see? Well, you're going to see a large amount of content about handling missing values, handling outliers, binning numeric variables, encoding categorical features, almost always encoding categorical features with one hot encoding, simple numerical transformations, among them things like scaling numerical features, and then pulling pieces of the data out. So what's the week of this date, or the month of this date, or the day of the week of this date? Now, all of these are important. All of these are necessary. Well, I take that back. Most of these are necessary for your model to even train successfully. Some of them are not strictly necessary, so it's helpful to understand when to do these. But this is not what I really mean by feature engineering. I think of this as almost my pre-modeling phase. It is feature engineering, but it isn't really about extracting signal. It isn't really about capturing business knowledge. It's more about getting my data ready for that modeling piece. Right? So keep in mind that my goal is to add signal to the model. So how can I go about doing that? Right? The goal here is, let's generate features that help the model find this signal. Let's help the model do things that it doesn't do naturally. And keep in mind, this can be very simple math. So some examples. Most models have difficulty with ratios. I may know that the ratio between two features is meaningful. So I spent some time looking at credit card fraud. One ratio that's really interesting is the amount of the purchase versus the available credit. Simply calculating that can help add signal. When looking at tree-based algorithms, boosted trees, random forests, what have you, they have a difficulty with simple subtractions, differences between features. So it can be really useful to simply calculate those differences. Okay, and so I do see a question, a really good question from Atanu. Does excessive feature engineering result in an overfitted model? It really depends. I'm going to be perfectly honest. I have a problem in feature engineering. I tend to create too many features. I would never recommend using all of the features you create. I really think you should use some sort of feature selection methodology. So create lots of features and then try to pare back the number of features. Too many features can create too many parameters in your model. If you have too many parameters in your model, you can absolutely overfit the model. It is also one of the reasons we use validation sets, is to try to prevent that sort of overfitting. But feature selection is a really important topic, just not a topic for this time. Okay, and then there was another question about signal. Just think about the purpose of the model. The model's goal is to make predictions. I just use signal as a shorthand way to talk about what the model's trying to learn. And keep in mind, my background is probability modeling. So I think of the world as a probabilistic state. And so there's noise around everything we're doing. So think about the signal as the true value before it's been messed up, disguised by the signal. So the signal is simply what the model is looking for, or what I'm trying to capture to be able to make my prediction. And so everything I do in feature engineering is designed to help the model find that, to pick out those patterns and make a better prediction. Okay, and then another question before I go on, asked about feature engineering and deep learning. This is an interesting topic. I know a lot of times in deep learning, we say feature engineering isn't necessary any longer. Neural networks are capable of effectively generating the features for you. Now, there's a couple of different pieces to this. It does appear in images and video. To a large extent, feature engineering isn't as important. When I look at things like text and audio, it does look like feature engineering is a little more important. I'm not really covering that here. One note to think about, when I started building models almost 15 years ago now, we were using neural networks at that time. We still did feature engineering. Neural networks, deep learning, they're thought of as the universal approximator for any function. So, okay, that says I don't need features. Keep in mind that says I can approximate any function. It doesn't tell me how many hidden layers I need, how many hidden nodes I need, how many parameters I need, nor how much data do I need to actually train all of that. So again, by providing good features to a neural network, I may be able to get by with a simpler network, which should generalize better. And in addition, I may need less data to get there. And in a lot of cases, data is a limiting factor. Okay, so let's move on and talk about some best practices. The first thing is think about your end result. Your end result is to put a model into production and allow the business to make decisions. There are things I can do in a modeling environment that are hard or nearly impossible to do in a production environment. That can be things as simple as Python makes this really easy, but all my features need to be generated in SQL on a database. Some things are easy in Python and very hard in SQL. Maybe your environment allows you to use Python. You have an Airflow job that generates your features. But then you have a question of some calculations are slow and some calculations are fast. What I like to do is set up as close to the production environment as I'm going to be. If I know my stuff needs to work in SQL, I'm going to do as much of my feature engineering in SQL as possible. Conversely, if I know everything's going to have to be translated into Java, as painful as that is, I'd rather work in Java and do my work that way to allow me to put that model into production. Now, the other choice is over the last year, year and a half, with Uber discussing Michelangelo, the release of Feast, you can always just use a feature store. We can put the data into the feature store. I can actually store features that have already been calculated and pull them out. They're still necessary to get those features in. So we know we want to work in as close to production as possible. Think about the data as it comes through. Unit test your features. You know what you're calculating, you know what you're trying to calculate. Make sure you can test that. This also has the advantage that I can test it in my modeling environment and I can test it in my production environment. One of the places I've seen feature engineering go wrong is when data scientists build their features and then hand it off to the data engineering or software engineering team for productionalization, only to have them make a slight difference in the way the feature is calculated that can impact the model's performance. So be able to test that, verify that it works. In a related sense, have a canary file. And by a canary file, I mean a set of observations that when you pass through your entire modeling process, you have a known result that comes out, a known prediction. So you can test both in modeling and in production that you're getting exactly the same result. Again, if you can't guarantee that you're getting that same result, you can't guarantee the performance of the model in production, right? So you can verify that nothing has changed going to the production environment. You can also verify that nothing's changed in the production environment. Sometimes something gets changed, something happens in the system. A file inadvertently gets updated. If you're running this on an ongoing basis, you can quickly determine that something's changed in the system. Now, this kind of leads back to the question about overfitting if I do too much feature engineering. At the same time, in a related sense, don't overclean the data. I've worked with some data scientists who never got to modeling because they were so focused on generating perfect training data. Your data is never perfect. Your data in production is never, ever perfect. Your goal is to as closely model that production environment as you can. Now, this isn't to say that if you identify errors in the data, you shouldn't fix them, but anything you fix in modeling, you also have to fix in production. If you can't fix it in production, it doesn't help you to fix it in modeling. And then the other thing is, sometimes those errors are themselves predicted. The best example I have of that is at one point in my past, I was working with a hospital system that was trying to predict severity of illness for patients when they were admitted from the emergency department to the regular hospital. One of the most predictive features was the diagnosis of the emergency room physician. Now, when you explain this to the hospital physicians, they get upset. And they get upset because the emergency room physician's predictions are not usually very good. But here's the problem. That emergency room physician's job isn't actually to diagnose the patient. It's to triage the patient and identify who's sick enough to need further help and get them to the right specialists. It turns out they're consistent in their diagnosis for severe illnesses. That consistency is a signal that the model can pick up and use to make better predictions. And so if you're worried about the data, you may exclude that feature because it's not clean, it's wrong. You may try to fix it in some way, but it turns out that that decision by itself is very useful. And so that's what I'm meaning by don't overclean the data, is that there's signal in that data. And a much simpler example is, what do you do about missing values? You need to impute something for a missing value for the modeling algorithm to use it, but be careful because there can be signal in that missing value. And so somehow either capture that there's missing value or do something so the model can pick up that this is an imputed value. And so that's the idea, is just be careful that you don't inadvertently throw away signal by cleaning the data. Okay. Now on to the fun part, the part I really enjoy, the examples. When I think about feature engineering, I break it into really three parts. Flat data, nearly modeling ready, This is that data frame that you're ready to send to scikit-learn or XGBoost or Keras. Okay, so maybe it has categorical variables that I need to do something with. Maybe it has some other variables where I'd like to do some of those ratios or differences or some other combinations. But it's mostly ready. Then there's multiple files that I need to join together. This could be as simple joins and I still get one row, or it could be a join that gives me multiple rows and I need to do some sort of aggregation. The most common form of this is where one of those tables that you're going to join in has time series like data. It has a time component to it. This could be transaction history. This could be sensor data over time. This is where I've spent most of my career, is working with this kind of data where we're taking in this data over time. This is where I really enjoy the feature engineering process. I think it opens up and it allows you to do some really interesting things that can identify that signal. Okay, so with flat data, we talked about this a little bit. With tree-based models, trees don't capture mathematical operations well, add differences and so on. Let's put them in. Let's see what happens. Let's add those values, not all of them. You get a combinatorial explosion. You end up with too many features. But let's add them sensibly. Most models struggle with ratios, so let's add sensible ratios. There was a question here about categorical variables. So categorical variables are very interesting at this point. Most of the time when you look up, you see one-hot encoding. Sometimes you see label encoding. So one-hot encoding is creating individual 1-0 indicators for each of the values. Very standard, easy to do with scikit-learn. Label encoding is for tree-based. If I simply convert it to a numerical value, so the first one I see is 1, the second one I see is 2, the tree is going to separate on them as it makes sense. So it's just a way to save memory while you build those models. Those are the most common. There's one challenge with this. Both of these techniques work really well when I have very few categories. So if I have 5 categories, I create 5 indicator variables, or I give 1 through 5 as numbers to XGBoost, it'll work fine. What happens if I have postcodes or country codes? They're still categorical. There's a large number of them. I'm not going to create hundreds of indicator variables. So there's a number of things you can do. One of the most common is target value encoding, which is saying, okay, for this particular value, for this particular category, let's replace it with the average target value for that category. This has some complications. It's really easy to overfit if I begin pulling data from the validation piece into the training piece. So I may need to only use the training data to calculate that target value. You could argue that there's a problem because I'm actually using the target for this particular observation in that calculation. So there's an enhancement to that called leave one out target encoding, where I exclude the current observation. There's also a problem that if I only see a given category a handful of times, what do I do with that? Do I trust that estimate of the target value? So how do I roll that up? But there's some really interesting ways to handle it with that. And then as we begin talking about time series like data, the way to handle categorical variables becomes even more interesting. We can pull in even more information about them and potentially replace them with something much more meaningful to the model. We talked about multiple files. They're all on the same level. We can do a simple join. Most of the time you've got different levels. So you could have patient visit, multiple patient visits per patient, procedures, medications, multiple procedures, multiple medications for each patient visit. So you need to begin pulling stuff together. You need to begin doing aggregations. If there isn't a time component, it's just simple aggregations. How many do I see? What's the most common? What's the total number? What's the average? These sorts of things. When there's a time component like patient visits, it becomes much more interesting. And that's what we're going to talk about during the rest of this. Be very careful when you begin working with a time component. It's really easy to effectively use future information to predict the past. So only use data up to that point to generate the features. Don't allow yourself to use data from the future. And then be very careful when you do that train test split. You can't use a traditional random sampling because you will end up with past data in the validation or test set, future data in the train set, and you'll effectively be pulling information from the future to predict the past. And so that's a really, really classic way to get target leakage in your model. That relates to Kundran's question, is it okay to create ratio features using the target variable? Keep in mind, the target variable you don't know at the time you're making the prediction, so you can't use the current target variable in your feature engineering for that observation. That's the exact same thing of effectively pulling future information into the past to make a prediction. Your model is going to fall apart in production. On the other hand, in this time series data, yesterday's value, if it's known today, is perfectly legitimate. Classic case, sales forecasting. I want to predict what sales are going to look like a week from today. Well, honestly, the best predictor for sales a week from today is sales today, or sales a week ago if I don't have today's yet. So you can use historical target variables if they would be known at the time of prediction, but you can't use the target variable from today. Okay. Anyways, this is a huge topic, especially how to set up the train test partitioning. I wrote a blog about this over a year ago, so you're welcome to take a look at this. We talk about customer churn and the various ways to do this. Okay, so let's work with a time component. There's a lot of things you can do. People talk about extracting the values. Extracting the various values to get dates and months. You can get quarters. You can pick up some relatively good cyclical behavior just doing that. But there's something else you can do, and that's recognizing that with cosine and sine, you can generate arbitrary cycles. So by creating features which are given by the cosine of the frequency time, the time since the start of the unit of interest, this could be week, this could be month, this could be year, you can actually let the model identify the cycles themselves. So it's a really interesting way to capture cyclical behavior and time components within your data. Now, keep in mind, this works really well for linear type models, SVMs, regressions, even neural networks. You have to be a little more careful with tree-based models, XGBoost and such, but it's still possible to do. Okay, as we begin digging into this, I want to stop right now as we're about halfway through our hour together and point out that a week from today, what I'm talking about here from a theoretical perspective, I am going to share Python code, pandas code largely, to do some of it. I can't do all of it, but we'll absolutely walk you through creating a bunch of these sorts of features and show you how I think about building them up. And we will have some cases where we'll even talk about capturing some of that categorical variables with these sorts of concepts. Okay, so let's think about one-to-many relationships. We have in this case, this is hard drive failure. If you're not familiar with Backblaze, Backblaze has released daily snapshots of all of the hard drives in their data centers, along with information about whether or not they failed. So if you're looking for interesting data to work with, there's a massive amount of data there. This is kind of the idea behind it. Individual drives, have they failed, and then daily write stats for them where you have some information. What was the date it was sampled from? How many writes were there? What type it is? And we'd like to be able to roll this up. So the first thing to do is simply look at those dates and begin pulling out things. What's the earliest date? What's the last date I've seen? How old is it? How long has it been active? What's the duration between the earliest and latest date? You can think of that as age. Looking at time periods. How many samples do I have? If it's a regularly sampled signal, like hard drives, it may not be that interesting. If it's customer behavior, how often have they visited the website in the last hour or the last day? How many different websites have they visited in the last hour and last day? And then the other thing is when you're dealing with this time series like data, rates of change are really interesting. The way the behavior is changing is really interesting. I have a little bit of a physics background, so I think of it in terms of velocity and acceleration, but it's how did these counts change over time? And then how did that velocity or rate of change over time? So is it increasing? Is it decreasing? And is that increase increasing or decreasing? So begin to think about building up features like this. Next thing is standard statistics work. What's the mean? What's the median? What's the sum over the time frame of interest? What's the minimum maximum? What do the percentiles look like? So begin pulling out standard statistics over times, over moving windows as well. So if I'm interested in making a prediction every month, what does it look like over the prior month? What does it look like over the prior 2 months? What does it look like over the prior week? I think someone just said run describe on feature. Effectively, capture that output. But we can take this a step further. The minimum and maximum is interesting, but it's even more interesting to think about when did the minimum and maximum occur? How long has it been since the minimum occurred? What was the last increase or last decrease? Again, remember those rates of change are really important. What was the first value? What was the last value? I think someone was talking about algorithmic trading in the chat before we began. Well, clearly the last value of a stock price is meaningful. So pulling out that sort of information. We talk about the statistics, we talked about time periods, but think about it, it's not just time periods. So what happened in the last week or the last month could be interesting. If I'm thinking about customer behavior, the last 5 visits might be interesting. Once I have all of those, how do those values change over time? How did this compare to the last time period of interest or the same time frame a year ago? And then once I have velocity, as I think about accelerations, and then we spend a lot of time talking about how to get categorical variables to numeric, but it can actually be interesting to take numeric variables and convert them to categorical variables. And the way I think about that is a string where if the last 3 events were all increasing from one another, I have plus, plus, plus. But if the two prior to that were decreasing, it would be minus, minus. So I end up with a string plus, 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 minus, minus. Then I can handle that as a categorical variable and begin allowing the model to look at those sorts of patterns that may be hard to capture mathematically. Now you can go much farther than this. There's a Python package called tsfresh. tsfresh is an approach to build a lot of these mathematical features, things like what they call absolute energy, looking at sums of changes, correlations between times, trying to capture the trends, doing Fourier transform, coefficients, and so on. So you can just import tsfresh and run that on your data. With the caveat, it can be a little bit slow. You're doing a lot of mathematical calculations. It may not work as well in production. Again, keep that in mind. But it has a lot of very interesting functions to summarize time series type data. In a very different sense, if you go and you look at the concept of statistical process control, this is a concept from industrial engineering. You're looking at whether or not a system is in control. So you may look at things like, in the time frame of interest, do I have any values more than 3 sigma from the mean? Or out of the last 3 values, are 2 of them more than 2 sigma from the mean? You can look these up. There's the Western Electric rules. If you do a search on Wikipedia, there's a description of many, many of these rules. You can try implementing those. Is the system under control is an important thing from a modeling perspective. Okay, now let's talk about categorical features. How do I handle categorical features? Well, I could do things like, how many times have I seen A in the time period? How many times have I seen B in the time period? Which is larger? Do I see A more frequently than B? How many different categories did I see? And then we'll spend a fair amount of time on this next week, but we can aggregate at the numerical level. So we can do things like, what's the average value of the rights when I see A? What's the average value of the rights when I see B? So we can take this in to try to pull additional information. Okay. So thinking about this, what I'm really saying in this case is group the features together, calculate these same features at the group level. So all of those statistics we talked about at a customer level, I may do it at when I have hard drives of type A or events of type A. Pulling that together. We can simply add these as additional features. It may be informative to the model. Please do feature selection. Absolutely lag these features. We're thinking about this not necessarily as a time series problem, but a time series like problem. But yesterday's values are meaningful. A week ago's values are meaningful. A month ago's values are meaningful. So once we've done these collections, pull in the values from prior observations for the same thing. But I now have a bunch of additional features. I now know what the mean was over the last week and this mean over a week, a month ago. I can build a velocity there as well. I can build an acceleration. I can build moving and weighted averages over the mean of this value from this week to last week to the week before. So begin building up those features to try to capture, again, the trends. That's what we're really interested in here. And going back to these group features, we can also build these up. And this begins to get into what to do in the case of categorical variables. Is I can think of a very simple difference or ratio. What's the current value ratio to the mean value. I could look at the difference. What is the current value minus the mean value? I can take it a step further because I can say, what is the current value minus the mean value divided by the standard deviation? And I now have something that looks like a difference from the mean, or a distance from the mean. In a statistical sense, is it less than 1 sigma? Is it more than 1 sigma? I can actually add this to my model and begin saying, okay, for all of the people in this group, how does this individual look in comparison to them? How similar or different are they? We can, of course, take the absolute value. Sometimes being 2 sigma away larger is interesting as opposed to 2 sigma away smaller. Sometimes it isn't. Sometimes all I care about is that they're 2 sigma away. We can do it in both ways. So this is the fun part. This is where we get to explore our creativity. We should try as many different things as we can. If you're spending a lot of your time trying 20 different models and trying lots of different hyperparameters, why wouldn't you try the same thing with the features? Why wouldn't you try spending time to capture additional information? So before I finish with a couple additional slides, there was a question, what should we do if there's more than one level or more levels that can be handled by one hot encoding? I mentioned it. There's a couple of different things you can do. There's things like target encoding. So there's a Python package, categorical encoders, that includes a targeted encoding and a leave one out encoding, which are ways to try to replace individual levels with a numeric value that is related to the target value. Be careful, read the documentation so you don't add target leakage, but there are ways to do that. So you can handle it that way, or you can handle it this way by replacing not with the target value, but with some other value that seems to be related to the category. So it could be, if I'm looking at customer behavior and I'm interested in postal codes, maybe I replace the postal code with the average value of spend in that postcode, right? There's lots of things you can try. So give it a try. We'll come back to categorical variables. It seems like there's a lot of questions on categorical variables. Something I want to make sure. Oh, and there's class imbalance in a feature. It really depends with class imbalance. I'm not as concerned about class imbalance, I think, as most data scientists are. Again, remember, I got my start building models for credit card fraud, where individual transactions had about a 0.1% chance of being fraudulent. So I was trying to identify very, very rare events. And I would do some downsampling to improve the ratio, but I was building models between 5 and 10% positive class. And you can do it. Accuracy is a horrible metric at that point. I'd recommend using something like log loss or AUC as your metric. They're less sensitive to these class imbalances. So you can get by with building models with highly imbalanced classes. Right. So this is the art part of data science. And I honestly believe this is where you can add the most value. Capture business knowledge, capture behavior you see in the data. Look at the data. So actually look at the data, line it up over time, look at it. Do you see patterns? If you're seeing patterns, you may want to try to capture those patterns as features to add to the model. Okay, so once again, this was a theoretical talk. a week from today, we'll share a Jupyter notebook with all of you. We'll walk through a churn use case. We won't finish the churn use case, but we will walk through creating some features using many of the techniques I've shared today. So there's the coding workshop. And then the last piece, the company I work for Rosgo, is focused on helping data scientists do a better job of feature engineering. And as part of that, we've released an open source repository on GitHub, feature engineering tutorials. It's all Jupyter notebooks with code showing many of these things. So if you're curious about what to do about categorical variables, there's multiple notebooks that show you the different ways to handle categorical notebooks. Take a look at them. It's not just the code, but it's also the explanation. They're meant to be useful to you. It's open source. I'm welcoming contributions, questions, suggestions for additional things. So if my kind host could grab that link and share it in the chat, that would be awesome. Thank you. Please go take a look. Okay, so I'm going to, since we have about 10 minutes, if people have questions, we can answer them. There's a bunch of things here. Okay, so feature store, a little out of scope for this conversation, but the idea behind a feature store is if multiple data scientists are creating the same feature, why have them rerun the same code? Why not capture the output of that from a production environment, store it in a database, and make it available to other people? So you can think of it as another database within your data warehouse or in a separate location that stores not raw data, but features, and makes it easy for you as a data scientist to simply go pull them and pull them historically so you can use them directly in your model. So converting nominal features using label encoding might confuse tree-based models. It's an interesting question. I'm not convinced it will, just because all tree-based models are trying to create splits. They'll find patterns if they exist. Right, tree-based models, random forest, XGBoost benefit from having lots of simple, small, stupid trees. So it should find patterns. It's never going to look for big segments. I don't think it should cause that much confusion. But again, there's no guaranteed right answer. Try it both ways. There's no reason that you can't try converting categorical variables multiple different ways and pick the one that gives you the best test set performance, right? The goal is test set performance. And people have asked about overfitting. That's the real key. Am I building good test set performance? As long as I don't have information leakage from the test set to the training set, if it's holding up in the test set, I can be reasonably comfortable it should hold up going forward. So there's a couple questions about sampling. I like stratification when I do my test train split for categorical. I just like guaranteeing I have the same ratio between true and false in that data set. And that also helps with imbalanced data. If you have very rare events, it's very easy to have very different statistical behavior. So stratification absolutely helps. There was a question about that imbalanced data set. Downsampling, I like downsampling better than I like upsampling. I think downsampling works when I have large enough data. Again, give it a try. Try downsampling at different levels. Try building your models without downsampling and see what gives you the best answer. Remember, data science is an art. There aren't guarantees for any of these. Try different things. Pick the one that works best. There's lots and lots of questions that are scrolling way too fast. Scaling features. Scaling features is an interesting thing. When I'm doing, how do I put this? I oftentimes do scale them, but I don't scale them because I think it makes a big difference to the model. Now, most of the models I build today are built with XGBoost or CatBoost. It's where I tend to get the best performance. Scaling doesn't really matter to a tree-based model. The reason I like scaling is that when I do a feature impact, it helps me understand the change and puts things in a similar sense, a similar scale. It absolutely can help in linear regressions to actually find a good fit. So if you're using linear logistic regressions, I'd absolutely scale. Neural networks, I'd absolutely scale. Tree-based models, I think it's more up to you.
Andrew, I think there were a couple of questions regarding the domain knowledge, right? There was a question from Gunjan on, let me just pull it up, how to improve domain knowledge because it helps to create new features from existing features. As well as there is another question on the similar lines. When domain knowledge is not there, how does AutoML, how do these libraries help?
Yeah, so those are both excellent questions, and I am a big fan of capturing domain knowledge and capturing that within my feature engineering process. And the real key is when we start as data scientists, we almost never have the domain knowledge we need. So we need to gather it. If you're in a business environment, there are going to be business people who have thought about and looked at the problem. Don't discount them. Some of their ideas may be wrong. They may not be data driven, but they may also have some very deep insight. So I like to work closely with them. I like to start just talking with them about how the system works. Document how the system works. Document how they think the data should look. Some of them have looked at the data before. That's beautiful. Some of them have never looked at the data. We take what we can get. But then go back. Don't trust what they say. Validate. I have the data. They told me things like this. I like to run simple statistics on the data. What's the average value? What's the average time between purchases? All of these sorts of things. And then go back to that business stakeholder and say, this is what I'm seeing. This agrees with what you're saying. This disagrees with what you're saying. And work in an iterative fashion. It serves really multiple purposes. The first thing is simple statistics handed back to the stakeholder, the business stakeholder, can be eye-opening for them. And it builds your credibility with them. They may learn more or they may explain more based on what you're seeing. You may get the, oh, that's this case. We do know that happens, that they forgot to tell you because it wasn't what they were thinking about. You just learn more. You're also now investigating the data and you're beginning to build your own domain knowledge. You're beginning to understand how the business functions, how the product process functions. Now you can begin maybe even doing additional research, Google it, find papers about it, pull up that sort of information and kind of work in that process. This feature engineering process is going to be iterative. You're going to try things, they're not going to work. You're going to pull them out, try different things. You're going to look at the data and say, wait, this is a really interesting pattern. Why is that occurring? This is how you begin to build the domain knowledge. And this allows you to ask better questions of the business to hopefully get better ideas from them. Was there another question that you saw? We've got about 3 minutes left, I know.
Yeah, so actually what we can do is we can see quite a few questions on categorical variables and time series data. So what we can do is we can save these questions and address them in the workshop, right? And so I'll make a note of these questions. Any other questions? There are a couple which deal with the dimensionality reduction. So there's a very interesting question about what's the difference between dimensionality reduction and feature selection. And on the same lines, how does the curse of dimensionality affect the feature engineering process?
Those are both very good questions. Well, they're both almost workshops in and of themselves, but we can address some of it next week.
Sure. Yeah, so this is again more of a business question. What is the division of labor between data scientists and people with domain knowledge? And again, is it not better to create features based on the business model and what it requires the prediction to be?
That's an interesting question. I think it's the first piece, what's the division of labor, is very dependent on the environment and the sophistication of the business itself. I do think it's changing as more and more people in business have an analytics background. A lot of what used to be the secret sauce of data science is being taught in business schools today. So more and more people in the business are capable of doing some of this. Onto the other question, it really depends. I do think there's a lot of value in computing behaviors that are business oriented. But sometimes there's some things that are either just really easy to compute and oftentimes are valuable statistical measures, things around rates of change, which may not be driven necessarily from a business understanding, are just driven by the nature of the problem itself. It's time series. How things are changing is just important. But it's a balancing act. If I had to make a choice, I'd take business oriented over mathematical. But if I have the time, I'd like to capture some of those mathematical trends. And then it also comes down to the nature of the problem. If I'm looking at sensor data for a manufacturing plant and I'm trying to understand failures in my plant, honestly, I'm going to be left with a lot of mathematical signal engineering type features because there just isn't that same level of business understanding of the problem. But at the end of the day, the goal is, can I make the prediction accurately enough for the business to get value out of it?
Sure. I think that answers Girish's question as well. I think most of the questions are on categorical data and categorical data in time series. So I guess, Andrew, we would be covering a large part of it in the workshop session, right?
Yeah, and I'll add a little bit more about just pure categorical variables because there's clearly enough interest there. So I'll make a minor modification to capture that as well.
Sure. Then in that time, we can take up any other unanswered questions in this session that are pending.
Yeah, very good.
Great. There is a kind of a practical question. I think there's just a minute to go. It's about R. So there's a question by Rong Lee. In university, R is widely used like forward elimination step function. It's hard to find a step function in Python. Is it necessary for us to use Python and R simultaneously? I think it deals with the different languages in production and what we use in data science as well.
I really don't want to get into the battle between R and Python users. I tend to use Python simply because my background precedes most of the machine learning, and I was trained in C. So Python is more comfortable to me. There's a lot of organizations that are very, very effective using R. They both have their place. And as the question points out, there are things I can do in R that are very hard in Python. And conversely, there's things I can do in Python that are very hard in R. As long as I can take that model and put it into production, I don't really care which one people use. I think they're both valuable. And again, when I'm doing really hardcore statistical stuff, R tends to have better packages. There's just no way around it.
I think we can stop our questions for now. We can take up the rest of the session rest of the questions as I discussed before in the next workshop. Thanks, Andrew, for the amazing session. It was very educational and very interesting. Quite a few concepts that we haven't come across before.